So in general, as we discussed before, even though momentum is conserved in pretty much all types of collisions, kinetic energy is not. But there is one type of collision in which kinetic energy is conserved, and that's called an elastic collision. Now, in the real world, a true elastic collision can only occur on a really small scale between subatomic particles. But there are collisions that occur on a larger scale that are almost elastic. So very little energy is lost to non-conservative forces. So if you think about objects that collide in a vacuum or objects that are colliding, sliding on a surface with minimal friction, those are collisions that are going to be near elastic, if not perfectly elastic. But in a lot of our problems, we can kind of simplify and just assume that a near elastic collision is for our computational purposes fully elastic. So I just want to show you some of the equations that are useful when solving problems with elastic collisions, and then go over an example. So momentum is conserved. Okay, momentum is conserved, and the equation that we get from momentum being conserved is if you have a collision between two masses with two velocities. So let's say we have m1 with velocity v1, and we have m2 with velocity v2. Okay, momentum is conserved, so we can express that as m1 v1. So that's the momentum of the first object, plus m2 v2, that's the momentum of the second object, equals m1 v1 prime. So that's the momentum of the first object after the collision, plus m2 v2 prime. So that's the momentum of the object, the second object after the collision. Okay, so this is our first equation. We can manipulate this a bunch of different ways. And sometimes if you have a situation where one of the objects is initially at rest, one of these terms will cancel out. So that's always useful. The second is kinetic energy. That's also conserved. Okay, so how do we express that? We say that 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Okay, so that's a lot there. And notice that 1/2 is common to all these terms, so you can cross those out if you like. You'll never really have to leave those in when you're looking at elastic collision problems, so you can simplify it as m1 v1 squared plus m2 v2 squared equals m1 v1 prime squared plus m2 v2 prime squared. Okay, so these are kind of the two most essential equations when you're solving elastic collisions. Let's take a look at an example problem where you'd have to manipulate them. So let's say that we have our mass m1 is relatively small. Let's say it's about half a kilogram. Okay, and let's say that it's moving with an initial speed of 4 meters per second. And it's going to strike a second object. Now, the second object is going to be much more massive. Let's say it has a mass of about 3.5 kilograms. And let's say our initial velocity is 0. Okay, so this object's at rest. So before you even start trying to do any calculations, it's important to think about logically what's going to happen. So we have a relatively small mass with a relatively small to medium-sized speed approaching a larger mass that's at rest. So kind of think about it, and as this mass strikes this second mass here, because this one's smaller, this mass is probably going to bounce back. It's going to have some final velocity that's directed backward. And maybe this object's going to start moving a little bit, but because it's much more massive, it's only going to reach, maybe a smaller final velocity than this initial velocity here. So let's take a look at it computationally and see if that intuition shakes out in the math. So we'll start with our conservation of momentum and conservation of kinetic energy equations. But notice right off the bat, they become a little bit simplified because v2 is 0, okay? So we can write m1 v1 equals m1 v1 prime plus m2 v2 prime, okay? And we can also write m1 v1 squared equals m1 v1 prime squared plus m2 v2 prime squared. Okay, make that actually look like an m. Okay, so there's a bunch of different ways that you can manipulate these equations, but sort of the most useful, I would say, is to try to get the m1s together. Okay, so in both of these we have m1 on sort of both sides of these equations. Then we have only one term that has m2 and v2 in it. So we can rewrite it. We can write m1, okay, times v1 minus v1 prime equals m2 v2 prime, okay? And we can also write m1 times v1 squared minus v1 prime squared, okay, equals m2 v2 prime squared, okay? So you might be thinking, oh, what's the good of that? Now, it turns out this is actually pretty powerful, pretty useful, because right here we have a difference of squares. So we can rewrite this second equation as m1 times v1 squared minus v1 prime. Oops, not squared. So v1 minus v1 prime times v1 plus v1 prime, okay? And then we leave the other side of the equation alone, so we have m2 v2 prime squared, okay? So we've basically just factored this as a difference of squares. So what we can do from there is we can take this second equation with the factored form and divide it by the first equation. And if we do that, notice we have the m1s on the left-hand side canceling, and we have this one term, v1 minus v1 prime, also canceling. So we're left with v1 plus v1 prime equals v2 prime. Okay, so that's a relatively simple equation. So if we want to know, for instance, what the final velocity is of each of the objects, we can take a look at this first equation where we don't have any squared terms. We can move that around a little bit. We can maybe take a look at this, this first simplified form, and we can plug this expression here, so v1 plus v1 prime, in for v2, okay? And what happens when we do that is we get m1 times v1 minus v1 prime equals m2 times v1 plus v1 prime. Okay, so notice now we have it all in terms of quantities that we know except for v1 prime. Okay, so we can use that to solve for v1 prime. We just have to do a little bit of algebraic manipulation. So if we distribute on both sides, we get m1 v1 minus m1 v1 prime equals m2 v1 plus m2 v1 prime. Then we can regroup and get our v1 primes together. Okay, so we'd have, let's see, so we'd have m1 v1 minus m2 v1 equals m2 v1 prime plus m1 v1 prime, okay? And then we can factor out a v1 prime, and we just divide the left-hand side, which we know everything, By the right-hand side, where the only thing we don't know is v1 prime, so we divide by m2 plus m1. And then we can substitute back in our quantities that we have here. So we have, let's run the calculation. So we'll do, so m1 is going to be 0.5 times v1, which is 4, okay, minus m2, which is 3.5 times v1, which is 4, okay? And then we're going to divide by m1 plus m2, so that's 4. We divide by 4, and so we get that v1 prime is -3 meters per second, okay? And then we can take that and plug that back into any of these equations, and we can use that to solve for v2, which winds up being v2 prime is about 1 meter per second. Okay, so notice that v1 prime is negative, which is kind of in line with our initial assumption. So m1 bounces back. So its initial velocity is positive, its final velocity is negative. And then v2 prime is positive, but it's a lot smaller than v1. Okay. So hopefully you could follow that. You know, obviously you can rewatch this a few times if you got lost in any of the math, and feel free to post any questions that you have.